In our last section, we're going to be talking a bit about formulas. Formulas are equations that relate multiple quantities that are typically represented by variables. Here are three examples that we would like you to know and be able to use if they came up in a word problem. You should know distance equals rate times time, that the interest equals principal times rate times time, and that profit is revenue minus cost. Even though there's multiple variables in here, for our purposes, these aren't going to break any of the strategies or rules we talked about for first degree equations. You're either going to be given values to plug in and then solve, or you are going to solve for one of them in terms of the other. Here are some other formulas that come up in geometry. I want you to just pause for a moment and see if you can think and recognize what these formulas represent. All right, unpausing, this ends up being the circumference of a circle. This one is the area of a circle. This is the area of a triangle. And this one is the volume of a sphere. Don't be alarmed by the squared or the cubed in the area of a circle and volume of a sphere formula. You won't at this point be asked to solve for r in either of those. If you were asked to solve some element of this, you would be given r and asked to solve from there. An equation that has more than one variable is also sometimes known as a literal equation. The difference between formulas and literal equations in general is formulas typically relate some known figure or some relationship that's always true, like distance equals rate times time or the area of a triangle. Literal equations that you will see might not be anything you're familiar with, or might just be some arbitrary collection of things to practice our skills. When someone asks you to solve a literal equation for a particular variable, just like solving our first degree equations before, our goal is to figure out what that variable equals. You just need to be comfortable with the fact that in solving for this, solving for p, we're going to write p equals, but p won't equal a number. It will equal an expression with these variables. Our goal is the same, get p by itself, and in this particular case we see fractions and we know how to deal with those a little bit more efficiently now. So let's multiply both of these by the least common multiple of f and p and q, which is just literally f and p and q. F, p, q on both sides. When we multiply here on the left side, the f will cancel out, just leaving p and q, right? F cancels with f. Here, when we distribute, I tend to not want to cross out letters because some students get confused when I cross that p out, that p is all sort of used up in the second step and doesn't apply, and that's not the case. That p will multiply both of those chunks. So in the first one, the p cancels out and leaves f and q. And in the second one, the q cancels out and leaves f and p. All right. Now we want to solve for p, so we need to get p all collected. So we're going to use our addition property of equality to subtract fp from both sides. Let me clean this one up a little bit. Okay. And so we have pq minus fp equals fq. This is maybe a little bit advanced at the moment, but if you think about this, maybe we could rearrange a little bit to make it make a little bit more sense. That if we had this here in a sense, or in an example where there were numbers, let's say it was 5p minus 2p. In that case, when we combine like terms, we think about subtracting those coefficients. Just because those coefficients in this are letters does not mean we can't do the same. So in this case, we would have q minus f times p. And in our future, what we just did is something called factoring. They both have a factor of p, and we essentially reverse the distributive property, but we'll speak more to that later. If we do this, then we have q minus f times p. We would divide by q minus f, that whole quantity, so that this cancels out, and we would be left with p equals fq over q minus f. And there's nothing much more we can do to simplify or reduce. And so that is our solution. It says p equals. We got to be okay with that it's not a number because our equation had multiple variables in it. This is not something we can solve for a number. Let's do a couple of word problems that involve formulas and give you a couple tips and strategies in dealing with those. So this first one says that a sum of $95,000 is split between two investments, one paying 6% and the other 9%. If the total yearly interest amounted to $7,290, how much is invested at 9%? So there are two different investments going on here, so two different accounts that we have to worry about. But even though in this section we're dealing with formulas and literal equations, if this involves solving, we're not going to want two different variables in whatever equation we try and solve. So let's try and stick with one. Let's think about what part of an interest problem that we're going to have to solve for, though. We know that interest is principal times rate times time. The question here says how much is invested. How much is invested in something? That's what principal represents. So that is what we want our variable to be in this equation. If we're solving for principal, then we must know some of the other things or something about some of the other things. So let's see here. If it says the interest amounted to $7,290, the interest then from the two accounts is adding up to that. So we want expressions for interest so that we can sort of use this 7,290. So if we want expressions for interest, then we want the principal, the rate, and the time so that we can use this equation, or sorry, this formula to deal with them. And that works out well because the question is how much invested, the principal. So let's start by saying the principal, P, is the principal of the account that we want to solve for. So is the principal, remember we always define our variables, of the 9% account. Okay. Now we know the sum is $95,000, and so we're going to take the other account and not make a new variable, but use our strategy from before, where if we take that P away from the total, that leaves us the rest, and the rest is the principal of the other account. And that account was 6%. Okay. All right, it said then the total yearly interest. So that means that the time must be 1. The rate depends on the account, and the principals we have expressions for, but all of those multiplied together gives us interest. And we know that the interest from the 9% account plus the interest from the 6% account is what equals the 7,290. Okay, so let's write expressions for these. The interest for the 9% account is P times the R for that account, right? The interest rate for that account, 9%. And a quick little tip, in any formula that involves a percentage, you have to put the decimal version of that percentage in, not 9, but in this case, 9%. That means 9 out of 100. That's 0.009. And then times the time, which is 1, because we're talking yearly here. All right, in the other account, we have the principal for that account, which is 95,000 minus P, times the rate, 0.06, times the time, which is 1, and this adds up to 7,290. Okay, so this would be the setup, a great start. We don't need to finish solving this together because we've practiced in earlier sections how to deal with equations with, multiple variables by combining like terms and distributing and doing some simplifying ahead of time. We know how to deal with decimals. If that bothers us, we could multiply this entire equation by 100 and get rid of those decimals. You have those strategies, so I'll leave that to you. But the setup is what we wanted to practice. Always declare variables. Don't make more than one variable if you're going to try and solve, so use strategies of the rest and things like that. And in these newer problems, dealing with formulas, you got to know the elements of the formula to keep track of. Before we get started on this problem, I would like you to pause and try it on your own for a few minutes. All right, if you tried this problem and were not successful, chances are the reason why is there are a lot of different elements of this problem, and it can be difficult to keep track of what you're trying to solve for and how to incorporate the formula. So it is definitely a distance, rate, time problem, right? There are distances, rates, times. So the formula in this section that we need to pay attention to is distance equals rate times time. I'm going to introduce you to something that will help you keep track of what you're dealing with and even give you a little bit of a flow of steps to follow in filling this out. So this table, it looks like this because we've got a column for distance, a column for rate, and a column for time. Problems like this are also often they come in two parts. They're either two people interacting with each other or one person doing two parts of a journey or something like that. In this case, Brett was going pretty fast and then he got tired and he was going slow. So there are two parts of his journey, a fast part and a slow part. Okay? So we're going to fill out as much of this table as we know. However, there are a couple key moments to doing a problem like this. I highly suggest that the way you start is by putting which of these boxes is what you're really trying to solve for. So if you read the question, or read the question, it was, how far has Brett ridden? Oh, I just realized I spelled Brett wrong the second time. Oh well. When he reduced his speed to 12 miles per hour. So how far had he ridden at the faster speed? So the 12 might distract you. That's not how far did he go 12 miles per hour, how far before he reduced his speed. So we want the fast distance. How far did he go at the fast distance? We want the distance here. So let's make that our variable. And here's where we get to start filling in stuff. Okay, so if you read through this, one thing you know is he was 20 miles per hour at that faster speed. That's a rate, so that's just straight up 20 there. Then he slowed down to 12, so that's the slow speed, that's 12. He went 70 miles on his bike. Well, that 70 miles was split up, and we don't quite know how it was split up. That's part of the problem. However, if we said that the fast distance was X, we know the rest was slow, so that comes up to that idea of the rest again, so we can take X away from the total, and that must be the rest. And here's where you have to sort of pause and not get too carried away. You might read 4.5 hours, but that 4.5 hours is the total again. That's the entire trip. So neither of these two time boxes that are missing are 4.5. So be very careful about that. The awesome thing about this table and about using formulas here is once you know all but one of any variable in a formula, you can solve for the other using your literal equation ideas. So if you took this equation and solved for t, so you divided by r, we know t equals d divided by r, and we can use that here to write expressions involving x for time. Okay, in this fast row, we know the time for that situation would be the distance for that situation divided by the rate for that situation. And in the slow row, we know again that the distance, which is the expression 70 minus x, over the rate divided by r divided by 12 is the time. So, recapping, if you ever know all but one of the boxes in any row, you can use your literal equation, your formula, to solve for an expression for the third or for the last. When you have the box entirely filled out, take a deep breath, reread the question, and ask yourself, is there some other relationship that we haven't used yet? And in this, we have not used yet that the fact that the whole trip took 4.5 hours. Well, that's a total time. That means the time that Brett was going fast plus the time that Brett was going slow totaled up to be 4.5 hours. And here's your equation that you can solve to find x, and x was the answer to the question. We were very deliberate about that when we first started our box, so solving this will give you that answer. I'm not going to do so at this moment. You have all the skills to solve equations with fractions and decimals. You could change this to 9 divided by 2 so that you could use only your fraction strategies, but I will leave that to you. Try to use this box. Try it a couple times on problems like that. It's going to come back to us at several points during this algebra course.